Awesome, Bob. Great job.
So we will present our thesis today, and the topic for our thesis is predictive security for quantum key distribution enabled 6G slices via multi-layer telemetry. So I'll start with a little bit with the background. As we are officially entering the angstrom era where transistors are made at atomic levels, we are already seeing AI companies building digital twins of humans, which have 70 to 80% of accurate human minds. We edge closer to digital immortality. We aren't just securing the data anymore, we are securing human consciousness, and the network taking that kind of data should have the robust security. That's where our QKD comes in. We believe QKD shouldn't just encrypt communication, it should also act as a live sensor and health for network. Yes, and our study is entirely controller centered. By focusing on network controller, we can see and understand the network health, and we can predict the vulnerabilities before that happen. So now we'll talk about a little bit about why we need QKD. Right now, our entire digital world relies on math, especially the difficulty of factorization by quantum advancements are making math-based security obsolete. To truly build a quantum-safe 6G network, we shifted from maths to physics. That's where QKD comes in. However, we still believe that the future 6G network will be the hybrid models. Then I will explain a little bit more about how the QKD works. As you know, the quantum computing is already threatening, and Shor and Grover's algorithms are already threatening to break our public key infrastructure. So we believe the MAT will no longer protect us in the future. We believe QKD is necessary, as in it is embedded in physical laws. So a QKD generates a secret key by sending the photons in a specific polarization state, and based on Heisenberg uncertainty principle and no cloning theorem, any attempt to even observe those things will damage the QKD key, which will eventually increase the quantum bit error rate and allow the corrupted key bits and detected discarded. So then we'll go towards the three converging realities we have. So the first one is 6G. 6G isn't just a faster internet, it provides critical technologies, powers the critical technologies like robotic arm surgeries and self-driving ambulance, meaning we need an ultra-low latency, and the security in these must be built in from the start. Then we have the quantum computer threat, which we have already explained, as quantum computers are currently threatening our public key infrastructure. That initiates a phenomenon of HNDL, harvest now and decrypt later, and the rogue entities are right now harvesting the data, so when they have the computational power, they can decrypt it later on. And then that's where our QKD comes in. We believe the data communication, which is secured by QKD, is very secure. So the core question is how the network security will actually function when all these three realities are combined. That's when we'll look into the QKD black box. We call it a black box. In telecom industries, usually treat QKD as a simple unbreakable box lock. You plug it in, it generates the key, it either works or it doesn't work. Our proposal is we make that black box as a glass box, so we can monitor the health of QKD variables, which can help us to detect and spot the warning signs if there's something wrong. So can QKD, our question is using this QKD health data, can we predict the attack before happening? Monitoring the stress of quantum variables system alongside regular traffic allows us to stop security threats before they get worse. So then we'll talk about the boundaries and system constraints. As you can see, our thesis was mostly focused towards 6G environment. It was inspired by TerraFlow SDN orchestration, fully synthetic literature constraint data, and QKD as a controller visible proxy. What was outside our thesis scope was full physical QKD validation end user mobile, PQC, and carrier scale deployment, because we didn't have time and resources to cover these topics. So we come up with 4 research questions. The first question is, can we predict the attack in near future in a multi-layer telemetry? The second one is like, what specific value QKD variables bring to the model? The third one is, how robust is our model under the shifted parameters regime? And the fourth one is like, what alert threshold is best optimized, and trade-offs between the lead time detection and false alarm. Then we have the physical to logical split. As we know, multiple 60 slices share the same physical infrastructure, but have entirely different security requirements. As you can see, so first I will explain a little bit about what 60 slices. 60 slices, you can be taken as a highway, which have different lanes for each car. For example, there's a lane for trucks and buses, there's a lane for car, there's a lane for bicycles. So that's exactly the concept in 60 slices. As on highway, the speed limit is different for a car and bus and cycle. The same thing happens here. In a classical, in a slice, which is normal standard consumer slice, we use it for best effort delivery. The threshold for alerts could be very high, and it can even fall back to classical encryption, where the critical healthcare slice would be protected, which should have a robust security, zero tolerance for latency, and the threshold should be very low. Then this is our system architect, our proposed framework. So as you can see, we have the first layer. The first layer is QKD infrastructure, where all the telemetries and raw variables are generated. Then we have the second layer. Second layer is data plane, where all the normal traffic telemetries are generated. And then the third one is our proposed security intelligence engine, where we take the variables from all those layers and we put them into our model, and then our model evaluates and generates the labels to predict the risk. And so essentially our security intelligence engine actually sits inside the ASR, which is automated security response. Once the label is generated for security, then ASR enforces a policy which was defined. And ASR is actually also the subpart of Teraflow SDN, which is the bigger, in simple terms, like a 6G brain, which deals with the pathway computation and other traffic engineering. Then we have the multi-layer telemetry space. So we divided our variables into 5 different families. So the first family, as you can see, we have network and service, where we have latency and jitter packet loss. Then we have cryptographization, where we have a handshake delay, QDEP. Then orchestration could have recomputation paths, security have failed authentications, route manipulation, and then QKD aware variables like quantum bit proxy, key depletion rate, key refresh rate. So we just wrote a few variables here, but there are many variables. We just try to give an example of it. And all these families goes into our risk index. So our risk index doesn't spike or goes to the threshold if there is a spike in one family. It has to be coupled with all the families, and then when it's inputted into the risk index, and then if the risk index reaches to the threshold, that's when the alert is generated. Then we'll come towards the data generation. We have, as you can see, we generated around 200,000 telemetry rows. We had around 155 variables, which we reduced it to around 76, because some of the variables were more of the physical part. And then we had around 3,313 episodes, which were spread over 8 distinct scenarios of attacks, which could be low distress, campaign reconnaissance, and etc. And we had around like 20% of it as an attack in our 200,000 telemetry. So because of the number of variables, our data set was quite heavy. And then we showed that how that each episode, which I defined earlier, is generated. So in each episode, we have in phase 1, the episode have a baseline values. then it goes up into the pre-escalation values, then the escalation values, and then it comes down to mitigation and recovery. So in each part there's a different value, but also it defines the type of attack. For example, you can see in the pre-escalation we have no slow attacks, but in escalation we have hardcore attacks like TDOS bursts. Now I will invite Ibrahim to explain more about the data generation.
Thank you, Omar. So this is our visibility engine. So when generating our data, so we try to avoid independent and identical distribution, IID. So because cyber attack is not just an ordinary event, they comes in campaigns. So another reason for avoiding IID is like it will make our data looks artificially smooth, because real world data is always full of noise. So then instead of doing that, we generate an episode of attacks in order to mimic the real world scenarios. So, and also you can also look at this formula. It looks like a very complex mathematics, but the idea behind it is very simple. So the formula is derived from established academic books on simulation models, time series, forecasting, and transition rules. So now I will try to explain the formula. So X is our input, then J is our telemetry variable, T is time, and E is episode. So like Omar said before, so we have a baseline. So B is our baseline, then we had phase intensity to heat, then we multiply it by transition functions. So then in order to mimic a real world scenario, like I said before, so we need to have stochastic noise, because network data is always full of noise. So it's never been smooth. So then later we had this coupling effect to it, because each variable, like each scenario must have an impact on each other. For example, let's say an adversary just try to load the system with the massive amount of DDoS attack. So then so that key depletion will drop, then this refresh delay, it will spike. So now, like Omar said when he was talking about the phases, so we have the telemetry from each we have data from each telemetry. So then you can see network stress, security anomalies, cryptography stress, then QKD health, then we also have service impact. So all of them were loaded to risk index, as he said. So then risk index, we now add weights to them. So but adding weights to them, those weights are not equal. So those telemetry that we are carrying heavy weights, they are the one that are related to direct attack. So such as like network stress and security anomalies, they carry 25%. The crypto stress and QKD health, they both carry 20%, because they are like our center of hypothesis. Then also this carry 10% service impact, because it's just like a normal standard network. So then from risk index, it now load it into our model. So then this, you can see the trend, it starts from the baseline, but immediately when it's we're about to cross the threshold, then the model will now start evaluating it based on the horizon time to measure the time. So then the output will now be based on the risk attack, maybe if it's 30 seconds, within high risk within 30 seconds, within 60 seconds, and also time to high risk. So then we have our model, but in order to train our model, we cannot just load a raw data into it. So we have to do feature engineering. So by doing feature engineering and cleaning the data, we eventually end up having 347 columns. So because initially we have around 76, 77 variables. So we end up having 347 columns. And then when we do ablation, because we have performed ablation as well, we removed those columns those variables that are related to QKD. We remove them, then we end up having 259 columns. So then we now know them, we train our data, our model separately on different ablation with different data set. So you can see we have logistic regression, which is our baseline, is a linear model. Then we have data required unit, which is a deep learning machine learning model, is a sequential learning model. And then we have SG Boost. So SG Boost is a machine learning model and it's non-tabular model. So then you can see the precision recall area under the curve here is approximately 67%. Then you see the recall is approximately 95%. But the problem with this model is like the false alarm was approximately 80%. So which means it's unusable for our automation security response. So this model is not trustworthy. Then we have the gated recurrent unit, which is deep learning model. So then you see the PRA you see of this one is approximately 95%. And then the recall here is approximately 97%. But the problem with this one as well is that the precision is around 75.2%, which means that this is a sequential model. It's called it's because, and also it have a 24 look back memory, which means it remember things. It have a very perfect memory. So it will just memorize the data based on their sequence, and memorizing every data, we all know that in machine learning. So that means like the model is liable to overfitting, and also it contains a lot of noise when it captures everything. Then when we come, so it's not really perfect. So when we come to XGBoost, which is our non-tabular model, you can see PRA you see here is approximately 97%, but the recall is lower than them. The recall is approximately 90%, which is 91%, which is not bad. But the very good part of this is like it reduced the false alarm from 80 to approximately 1.6%, which makes it operational balance for ASR to use, and it's much more trustworthy. So now that was the answer for our research question 1. Then to talk about research question 2, we compare KD aware telemetry and telemetry with the classical telemetry. So then you can see we train each model based on, so you can see the performance with QKD is the orange, then with classical baseline, that was blue. You can see the performance here, you can see, and then you can see the accuracy, the F1 accuracy, then you can see how QKD have an impact. So then the QKD aware telemetry consistently improves predictive security performance. This is our answer for research question 2. Then we talk about this, we try to talk about the, to check the early warning, to predict the early warning. So then our linear model, it's predicted its own at 11 steps, which is because 55 seconds rather, based on 272 alerts. But the problem there, like I've been saying before, is like approximately 80% of the data that he captured, of the alerts that he predicted was false alarm. So then you can see like it's like 8 out of 10 of 10 are false alarm. So which makes it operational unusable. Then for our non-linear model, its own prediction was like 20% of lead time to attack. Then based on 204 attacks that it captured, alerts that it captured, then approximately 16% of these are false alarm. So I just want us to read the quotes beneath this slide. It's like, it said that a 55 seconds early warning is useless if it triggers on 80% of benign traffic. XGBoost sacrifices 35 seconds of lead time to achieve near perfect noise suppression. So this is our answer for research question 4. So then to talk about we also check the robustness of our model to know how good their performance is. So you can see how it moves from original to strong. So in each step, it increased. So you can see how the mean risk index were increasing, and then the target positive rate too. They are increasing in every step. You can see that it increased from 31.6 to 31.8 on this one percent, and also 18.9 to 34.1%. So then continue on shifted parameter regime. So I've talked about this one. Then you can see the accuracy of XGBoost here is like between 91 to 92, that's 91% across on scene parameter shift. So then you can also see the perfect detection here. You can see QKD instability also predict its own early warning of lead time, or rather, which is 15 seconds early, and then the key pull, the pressure is 20 seconds, Then DDoS like burst is 22.5 seconds. And then you can say like, nothing is perfect in this world. Everything have their own vulnerabilities. So our model struggle to detect this, can predict stealthy reconnaissance and also credential abuse. But we cannot say like because when we find out, we first like, okay, what happened? Then later when we deep down, it's like our model show honesty there, because what we were proposing was like our model should be on architecture, infrastructure and transportation layer. But what these attacks are, campaign reconnaissance and credential abuse, they are application layer attack. So they are kind of low and slow probing. So, but it's very difficult also. Our model struggle to predict this attack, although even SG Boost that perform better, it also dropped below 36%. So now to talk, that was answer for our research question 3. Then to talk about this hypothesis, then we use QKD telemetry. We show how it will improve the performance of the between the versus classical. So it's improved the performance. Then we use temporal engineering improve the performance of XG Boost. Then we talk about this, talks about the operational trade-off, how XG Boost trade-off 35 seconds by reducing the false alarm rate to 1.6%. Then for the threshold, actually there is no universal threshold for the system. So now to finalize the results, so research question 1 and 3, we see like how precision recall area under the core was like for XG Boost was approximately 97%, and then the robustness of which the accuracy of F2 score is like 91%. Then how, so this was answer for research question 1 and 3. And then the research question 2, how KD aware telemetry actively improve the predictions. And you can also see the key pool depletion and path availability. They both have like the variance of approximately 40% of their hypothesis. Then you can see the trade-off here. XG Boost have like it sacrificed 35 seconds of this trade-off, then by reducing the false alarm rate to 1.6%. And then during the ablation as well, you can see that each episode, like between 15 to 22.5%, the trade-off like around 7.5%. Then to 7.5 seconds. Sorry. Then to talk about the future work, so we need to increase the ability of our model so that it will not be blind to stealthy reconnaissance. So it can, at least it can predict an attack of stealthy reconnaissance. And also we try to test bed on Teraflow SDA. And also I will hand over to Omar.
So yeah, now I'll just talk about the limitation very quickly. So as you know, our limitation was synthetic data restraint. We generated a very Python-based synthetic data which didn't have QKD, no direct measurement from the actual physical QKD infrastructure. And for a scale constraint, we simulated only a 60 slice, so we are lacking the adversarials of a real world environment. And for mitigation, our work was like early warning feasibility, and we supported the alert prioritization, but it does not implement the fully autonomous live ASR execution. So for the final, we'll just, to wrap things up, our original claim was like, okay, can a QKD-enabled controller-centric framework predict the near future attack risk? And we think it was somewhat proven within the limited constraint and lab environment. We can say that like by using QKD health metrics and temporal XG Boost, we got around 20 seconds median lead time and 90% recall with near zero false alarm rate. And for future work, we want to, we think that we want to implement it into 5G RAN and Teraflow SDN. We want to test it so we can have it. These are all open source softwares. That's for the future work, and as also we said, like we want to improve for the stealth reconnaissance and credential abuse We also want to check if our work was in line with the industry standards. So we will send this to for review. That's pretty much it. Yeah, thank you, and we'll welcome any questions if you guys have.
So thank you very much for interesting presentation. So I'll leave for the talks now.
First of all, I just want to say really nice thesis, really well structured, really interesting.
You
Strong.
can come out if you want.
No,
Or you can, yeah, but you can just speak louder.
Oh yeah, so I really like how you're comparing different models on different configurations, and I really like the fact that you address the main limitation, which is you're using like literature constrained synthetic telemetry environment. You make that clear in your thesis. So overall, really great thesis. If you want to say, have some words.
Yeah, same for me. So it was a very interesting thesis to read. Like the topics are very interesting about KOKD and 6G networks and the future of